In this video, we are going to investigate mostly number properties. And properties of numbers are basically they're like rules that describe how numbers behave when you do certain things, when you perform mathematical operations. And several of them are so important, so fundamental that they even have special names. So we're going to talk about four of them in this video. They are called uh, closure properties, identity, associative, and commutative. So I'll talk about each one of those in depth, specifically with regards to addition, because that's what we're discussing right now. We'll also talk about inequalities. So let's start with closure. We call it the closure property of addition. Closure property of addition. It's really as simple as this. If you remember earlier in a previous video, how I defined what a whole number is. Remember, it's those numbers 0, 1, 2, 3, 4, 5. The closure property essentially states that if you were to select any two whole numbers, their sum would be another whole number. Closure means that if you start with two numbers of some category and you do the operation, then you end up with a number in that same category, or we'll call it a set, because we've been working with sets. If you start with a whole number and you add another whole number, you're going to get another whole number always. So how we say that then, how we speak it mathematically, is we say that, I will paste it right here. We say that the whole numbers are closed for the property of addition. Whole numbers are closed for the property of addition. Again, closure means if you're going to do this operation, you're not going to end up with a different type of number. So let's investigate to make better sense of this. Let's investigate some other different types of numbers. Okay, so let's say we're going to investigate specifically not just whole numbers, but odd numbers, 1, 3, 5, 7. So let's just investigate odds, which are 1, 3, 5, 7, etc. And I'll ask the question, are odd numbers also closed under addition? Now let you think about that for a second. Again, are odd numbers closed under addition? Well, you can test this out. Pick two odd numbers. Let's say 3 plus 5. What do you get when you add 3 plus 5? You get 8. I'll ask the question, is that another odd number? No, 8 is an even number. So what does that mean then? Odd numbers are not closed. The set of odd numbers is not closed under addition. And again, the reason that is because if you take two odd numbers, two numbers from that set, add them together, you get another number that's outside of the set. All right, so that hopefully helps you understand what this idea of closure means. If you like a formal definition, I think sometimes it's nice to see that formal definition as well. You can see it here. For every pair of numbers in a given set, if an operation is performed and the result is also a number in the set, the set is said to be closed for the operation, all right? And it may be even helpful to you to draw a circle, right? Consider that last example. If this is the odds, you got 1, 3, 5, 7, 9, and you add 3 plus 5 and get 8, that number belongs outside of that circle, right? It's not within the set. So if circles help you do that, because that helps us examine the idea of sets, then do that. So here are a couple of questions for you to consider regarding closure. And so go ahead and pause the video and consider these 3 questions. 1, the set of even numbers for subtraction, is that closed? The set of odd numbers for multiplication, is that closed? And then, can you think of an operation on whole numbers that is not closed? So go ahead and pause and consider those questions, and then come back. So let's look at that first one. The set of even numbers for subtraction. We're asking, is that a closed operation? An even number minus an even number. What do we get when we subtract an even number minus an even number? Well, let's pick some even numbers. We could go 8 and 6. 8 minus 6 is 2. Do we get an even number? We do. Well, we know that one example doesn't prove that it's true for everything. So we have to consider some more. So let's pick another one. Let's pick a big even number. 100 is an even number, and 10 is an even number. If we subtract those, we get 90. It's also even. Can you think of any example where you would not get an even number? You might be wondering, well, what if we picked 4 minus 6? In this case, we actually get a negative number, a number 2, negative 2. Or another situation you might be wondering about is, what if I pick 8 minus 8? 2 even numbers get 0. Are these even? Technically, they are. They are even numbers. If they're not odd integers, we'll talk about integers more, then they are even. So the set of even numbers for subtraction, yes, it is closed. Okay, it didn't say it had to be positive. It just said it had to be even. How about number 2, the set of odd numbers for multiplication? So number 2, if we take an odd times an odd, that's what we're checking. Do we get an odd number back? Well, let's try. So an odd number, 3 times an odd number, 5. 3 times 5 is 15. Is that odd? Absolutely. Okay. What if I pick a couple different odd numbers? 1 times 73. Those are both odd. I get 73. Is there any situation where you would possibly get something that's not odd when you're multiplying? I can't think of one. No. So this is also closed. The set of odd numbers is closed for multiplication. So we've seen a couple that are closed. Can you think of an operation on whole numbers that is not closed? Meaning, if you take a whole number and do something to it with another whole number, do you get something that's not a whole number, right? That's not a whole number. Can you think of an operation? The first one that comes to my mind is division. Division with whole numbers is not closed. Here's an example. 2 divided by 3. What do you get when you divide 2 by 3? It's actually a fraction 2/3, not a whole number. So division is an example of an operation under whole numbers that is not closed. So that's what it means for a set to be closed. You do something to it and you get another number in the set. Another property I want to talk about is called the identity property. The identity property, and specifically for addition. Identity property for addition. So what do you think of when you hear the word identity? I think of superheroes. I think of Superman, his secret identity, right? Is Clark Kent, Batman, Bruce Wayne, right? So the identity is who they really are, right? And so numbers have identities. It's what their value is. And so if we think about these properties, and you think about identities for addition, is there some number that you can add to any other number that doesn't change its identity? If I take some number, let's just say 5, it's a whole number. Is there something I can add to it where it doesn't change the number? It still gives me 5. 0, right? 5 plus 0 is equal to 5. So what that means is we say that 0 is the identity for addition. 0 is the identity for addition because when it's added to another number, there is no change. All right. Formally, we can state that like this because 0 is the only number that will do this. And you'll see this is how we often define these properties. Identity property for addition. For any whole number b, that's saying that we are using this variable b to be representative of any whole number. Stick any whole number in there, and this will work. 0 plus b is equal to b plus 0, which is equal to b. You add 0 first, you add 0 second, it doesn't matter. You're still going to get b as the solution, the sum. And 0 is the unique identity, which means it's the only number that works for. The next property that we're going to talk about is called the associative property. Associative property for addition. And if we just think about the word associative, I often think about, it's like, who do I want to be with? Who do I want to associate myself with? These people, right? My friends. Who do I want to group myself with? Those are my associates. Those are the people that I want to associate with. Numbers kind of work the same way with this associative property. And I'll give you an example here. If we want to add 3 numbers together, let's say 5 plus 7 plus 3. If we want to add 3 numbers together, there's this number in the middle, right? 7 is in the middle. And what 7 can really do is it can choose which of the other 2 numbers on either side of it wants to associate with. Does it want to associate with the 5 or associate with the 3? And we can really choose. How do we do that with a notation? We use parentheses. The symbol of parentheses groups numbers. And so we can say 5 plus 7, put parentheses around that. We can group it, the 7 with the 5, or we can take those same 3 numbers, 5 plus 7 plus 3, and we could say we want the 7 to associate with the 3. And all that means is which numbers are we going to add first? We can add 5 plus 7 first, which is 12, and then add 3, which is 15. Or we can add 7 plus 3 first, which is 10, and then add the 5, which is also 15. That's what the associative property says. It doesn't matter. 12 plus 3 is equal to 5 plus 10. They both equal 15. And you may say, well, why does this matter? Why are we learning this? What we're going to see later is that when you start to think about ways to add, especially if you want to do mental math, mental addition, sometimes you look for groups of numbers that pair well together. And 7 plus 3 pairs well because it makes a nice, neat 10. And so that's where you might want to use or apply this associative property. So here is the formal definition for the additive or the associative property for addition. For any whole numbers, A, B, and C, A, B, and C, or any whole numbers you want, A plus, the formal way we say this when we group numbers together is quantity. We say the quantity B plus C. A plus the quantity B plus C is equal to the quantity A plus B plus C. That's the associative property. The next property we need to discuss is called the commutative property. The commutative property for addition. Notice these are all about addition. So when you hear the word commute, what do you think of? I know what I think of. I think of my drive to and from work every day. Maybe it's for you, it's your drive to and from school. So when I think about commuting, I drive one way and then I turn around and I drive back the other way, right? I start and end, and then I end and I start over again, right? It's the same path, but it's just in different directions. With numbers, we can switch the order in which we add them. If we add 2 plus 3, that's the same thing as adding 3 plus 2. It's the same two numbers. We've just changed the order in which we do them. And that is an important property of addition. We can move numbers around an addition sign. The formal definition, as you can maybe guess, looks like this. For any whole numbers, A and B, again, there's our two numbers, doesn't matter what they are, A plus B is equal to B plus A. And we saw this example right here. Pick any two numbers, add them, and that is going to be true. One thing to note is that young learners work on internalizing sums, especially early on, of numbers between 0 and 9, right? Do I know instantly that 3 plus 8 is 11, or 7 plus 6 is 13, or 9 plus 9 is 18? This chart shows that, right? It's this grid. And the commutative property helps us cut those in half. If we think about what is 3 plus 8, 3 plus 8, we see it's 11 here. But if we look at 8 plus 3, we see it's 11 here. So if young learners can understand that 3 plus 8 and 8 plus 3 arrive at the same sum, then wow, it makes it seem much less daunting of a task for them to internalize all of those sums. There was research done, really powerful research done about students who developed at a young age good number sense. And if you consider students who might have to add 3 plus 8, these researchers found that there were really 4 strategies that students used. One was counting all, right? So a student might say, okay, I know I have to take 3 things and add it to 8 things. And so they would just sort of count them all. And they would say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And that's how they would get their total. Another strategy that students used was saying, all right, I'm still going to use a similar strategy, but it's called counting on. So they start with the first group and say, okay, I already know I have 3. And if I need to add 8 to that, 4, 5, 6, 7, 8, 9, 10, 11. So that's another strategy. That's a slightly higher level thinking strategy. And one thing you might consider with that one is it's a lot easier to do the count on strategy if you flip-flop these, if you start with a bigger number. If you start with 8, 1, 2, 3, 4, 5, 6, 7, 8, and have to add 3, you already start with 8, and then you only have to go 9, 10, 11. So you can see how the commutative property can help with that. Now, there were still higher level thinking skills beyond those strategies. Eventually, one of the things that students would get to is using, and we're going to talk about this later in this chapter, but what's called decomposition. And eventually you want to get to the point where you say, well, actually, I know that the number 3 is composed of 2 plus 1, right? The number 3 has this value 2 plus 1. And then if we think about that associative property that I introduced a minute ago, think about how the regrouping there helps with coming up with nice, easy numbers. 8 plus 2 is 10, plus 1 is 11. And so higher level thinking strategies involve taking numbers and decomposing them, breaking them up a little bit. But they all come down to these properties that we are learning right now. And so that's why it's really important for young learners to internalize these properties. So we've talked about the identity property, the closure property, the identity property, the associative property, and now the commutative property. And then finally, what we'll talk about in this video are the inequality of whole numbers. Inequality of whole numbers. And this is something that is sort of intuitive in terms of where numbers fall on a number line in order that you count them. And so what I'll do is I'll just start by sketching a brief number line. So just going to copy and paste that. Starting with 0, because we're talking about whole numbers. And again, a number line is formed when we just start with 0 and we count up by ones. 0, 1, and then we just keep on adding additional numbers, add 1, and 1. And they have to be spaced equally. That's an important part to any number lines, that they're spaced equally. And we call this a unit segment. A unit segment. And the inequality of numbers is really stating that numbers can be larger or smaller than other numbers. And so we can see right from our number line that 3 is less than 5 because it comes before it on the number line. It's to the left. We've been working a lot with our base 10 pieces and using those to provide a link between the area model and linear models can be very helpful, right? Students can start to see if you use base 10 pieces, draw them right on a number line. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we start to build a visual understanding of, again, how areas and number lines, linear models can be linked together. Now, you are probably familiar with symbols that illustrate inequality. They are the symbols that look like this. Those might look familiar to you. So this symbol means is less than. This symbol means, if we put the line underneath it, is less than or equal to. This symbol means is greater than. And this symbol means is greater than or equal to. And we can use these symbols such as this. Is less than. 4 is less than 9. And notice I use that word is. That's a really important word when we start to define these symbols, because it really turns it into a sentence. 4 is less than 9. We can also flip that around and say 9 is greater than 4. And so if we want to look at definition, a formal definition of these inequalities, specifically the inequality of whole numbers, it really looks like this. And we'll investigate these more in the future. For any two whole numbers, m and n, m is less than n, written using these symbols, if and only if there is a non-zero whole number k such that m plus k equals n. Sometimes with these formal mathematical definitions, you need to read them several times, look at them, stare at them, right? For them to start to make sense. Really analyze your own thinking here. There is a non-zero whole number k such that m plus k is equal to n. Consider our example here. 4, in this case, is the m. 4 is less than n. If and only if there is a non-zero whole number k such that 4 plus k, 4 plus this k number that we're going to try to figure out is equal to 9. Can you think of what number goes in there? Yeah, there's a positive 5, right? A non-zero whole number means it's going to be a positive number. So that's how we define inequality. 4 is less than 9, and we know that because if you think about where those numbers would appear on a number line, here's 4, here's 9. In order to get from 4 to 9, I would have to add 5. One of the things that I'm hoping you are taking from this class and these videos is these formal definitions and how we have to start viewing some operations and ideas of mathematics that we previously might have just taken for granted.